Hello and welcome to this IROS 2021 presentation about our work at UCL investigating a caging-inspired gripper design. This work is motivated by robotic grippers for pick and place of items, and in this presentation I will be discussing some background, followed by a proposed gripper design and experimental validation. The two videos shown on this slide demonstrate the classic robotics problem of bin picking. Shown on the left, Ocado research demonstrate bin picking and sorting into shopping bags. Notice how the objects in the bin have random poses and are chaotically assorted. Next, we have a research project called DexNet. Here there are two grippers, suction once again, and also a parallel jaw gripper. The robot is able to choose between them. Suction and parallel jaw gripping are the most common sorts of gripping in industry due to their simplicity. However, there are many kinds of gripper. The research literature is filled with a wide variety of gripper designs. Some are highly complex and modelled after the human hand, with many actuators and a huge space of possible grasps. However, grasp planning for these grippers is highly complex. On the other end of the spectrum are soft grippers, designed to be easy to control and take advantage of compliance to adapt to object shapes. Between the two extremes is an attempt to add enough actuation to increase grasp variety, but not too much to greatly complicate grasp planning. Overall, there is a huge variety of grippers to choose from in the literature. So, given the wide variety of grippers to choose from, what grippers are being used for bin picking? Amazon ran 3 international challenges from 2015 to 17 to test teams' abilities to pick and stow seen and unseen items. Most of these teams came from universities. However, despite this, all the challenges were won using a robot with a suction gripper, such as the most recent winner, Cartman, shown in the video. Their gripper design had a swivel head, a suction gripper on one side, and a parallel plate gripper on the other side. Similarly, the team from MIT and Princeton used a suction gripper and a parallel plate gripper in tandem. You can see the head of their design had both in the final frame of this video. Overall, suction and parallel pinching were the most successful technologies. How about more recent industrial developments? The commercial Right Pick 2 uses a suction cup to lift objects and then secures them with 3 fingers. Similarly, the Kindred Auto Grasp uses a suction cup and then engages 2 fingers in a parallel pinch. Therefore, you can see some industrial designs are once again using suction and 1 degree of freedom mechanisms for pinching. This is due to the simple grasp planning. Simplicity bears out when you want a reliable production. This work looks at a variant of the bin picking problem, where the task is to move grocery items such as fruits and vegetables. These items offer some unique challenges, which make suction and parallel jaw grippers less suitable. For example, suction cannot make a good seal on porous surfaces or perforated plastic films. Net bags can also be a problem for both suction and parallel jaw grippers, since the center of mass changes as the object is lifted, which can wrench it out of the grip. Crucially, these items need delicate handling, as they bruise and damage easily. Therefore, we might need to look to alternative grippers for grocery handling. For these reasons, soft grippers have mostly been tested in this domain. Soft Handler is a 4-finger 1 degree of freedom soft gripper where all the fingers curl together. In an experiment to pick and place plastic fruit from a cluttered container, the grasping success rate was 69%. In a proposed benchmark for bin picking grocery items, the authors tested 4 state-of-the-art soft grippers, all 1 degree of freedom. They defined 3 different levels of clutter, mentioning how dense packing in containers is often a key challenge in this domain. Shown on this graph are the success rates for each item averaged across every trial, with each gripper a different color. Here is the 50% mark. Clearly, picking grocery items with these grippers is not yet achieving high success rates. Taking inspiration from the simple grasp planning of suction and parallel jaw grippers, is there a way to achieve this with more complex grippers? Perhaps the concept of a cage is a good starting point. Caging means to prevent an object escaping. The object may be able to wobble, move, or rotate, but if it is caged, it can never escape. Here's an example of caging in 2D, and now a similar cage in 2.5D. Caging can use more than 3 agents and be non-redundant, where every agent is needed, or redundant. Caging may involve the environment or rely on gravity. Caging has been applied to grasping before. However, completing a cage in 3D is a significant challenge, so most work focuses on the 2.5D case. Fingers are typically pins, similar to how they would be modelled, and often simple actuation is used. Here we see some examples from the literature of caging grasping in 2.5D, where the object is squeezed and friction used to stop it falling out of the grasp. Work has also been done at 3D cages of specific objects, using compliant foam for example. However, it's still a significant challenge to cage all objects in 3D. What are some conclusions we can draw from the literature then? Grasping success rates for grocery handling are not yet very high, and state-of-the-art grippers for bin picking lack diversity and suitability for the task. Meanwhile, caging offers a conceptually simple but analytically complex method of grasping. Therefore, a novel approach to grocery bin picking could combine a medium complexity gripper, which uses an approach inspired by caging, with flexible fingers to enable more delicate grasping, and long fingers aiming to cope with densely packed bins. Here I present our proposed gripper. It has 3 flexible hooked fingers and a movable palm. It has 3 degrees of freedom, firstly finger lean, then finger tilt, and finally the movable palm. This gripper aims to use its fingers to get underneath objects, and then move the palm forwards to meet the object. Here you can see some example grasps. The fingers hook underneath, and the palm presses from above. Gravity is the key force to overcome in picking an object up, so this design directly uses geometry to oppose gravity. In the grasps shown, the bell pepper and broccoli are caged, and cannot escape without pushing aside a finger. However, the cucumber is not caged, and could slide out lengthways. Despite this, the palm generates a tight grasp by pressing from above, pushing the object into the fingers. The fingers are also simply flexible steel cantilevers. Not only can they bend to adjust to the shape of objects, but they can also flex like a spring to imbue grasps with elasticity. In some sense, it is an alternative approach to a parallel jaw gripper, which squeezes objects on the sides in the horizontal plane. Here, objects are squeezed top to bottom in the vertical plane. The ambition is simple grasp planning, where objects are all grasped in a similar manner, whilst being able to cope with the required variety of objects. In order to determine if this design is useful, we would like to answer 2 key questions. Can we create stable grasps, and can we pick a variety of objects? 2 experiments were done, one to answer each of these questions. The first experiment used the object sets shown on the right. There are 6 categories of elementary shapes, such as spheres and cuboids, and a small, medium and large example for each. To give an idea of scale, the small cube has 50 mm side lengths, the medium cube 100 mm, and the large cube 155 mm. These size choices stretch the limit of the gripper. So the first experiment wants to test to see if grasping is stable. Hence, grasps are tested with 3 disturbances. Firstly, disturbance X was applied with a 5 Newton spring in the most stable direction. In the example here, this direction is opposed by 2 fingers. Next, disturbance Y was applied with the same 5 Newton spring in the least stable direction. Here, this is opposed by 0 fingers, as the object is not caged. Hence, the grip must have enough friction to resist this Y disturbance. Finally, we have disturbance Z in the direction of gravity. This was achieved by adding weights to the objects. For the medium and large objects, 1 kg was added, and a 10 Newton disturbance. For the small objects, 500 grams was added in most cases, but some were too small, so only 300 grams could be added. Here is a video of the experiment. A human operator controlled the gripper, grasping from above, closing the fingers, and engaging the palm to get a stable grasp. Objects were picked from stands, and then the spring was used to apply the X and Y disturbances. The Z disturbance was then added, and the process repeated. This is the table of results from experiment 1. To understand this table, Let's first look at the top corner, with the row labelled sphere and the column small. These data points refer to the small sphere. Next we have the 6 fields. Each of these is scored out of 10 grasp attempts. Looking at the colour key, pale blue indicates 10 out of 10, every grasp succeeded, whilst dark blue indicates 0 out of 10, every grasp failed. In the column headings we have could the object be grasped, and if so, could it resist the X disturbance, and then the Y disturbance. There were 2 rows, one for the normal object, and one for the object when weight was added, the Z disturbance. Now let's look at the whole table. The first thing to notice is that the sphere and cylinder sideways had the worst performance. These were the only objects with rounded bottoms, and the metal finger hooks could not get a good grip on these surfaces. When weight was added, the flexible fingers were not stiff enough to trap the objects. Notice all of the spheres failed under disturbances when weight was added, even though the medium and large spheres were both completely caged. This was due to the fingers bending too easily. The next feature is the relatively poorer performance of the very small objects. This makes sense as these objects pushed the limit of what the gripper could handle. The small sphere and cube could actually fall out from between the closed fingers of the gripper, which is why these are the only 2 objects to have failed grasps without any disturbances. Finally, all the other fields are almost exclusively 10 out of 10, showing the excellent performance and grasp stability on flat bottom objects. The second experiment aimed to test the gripper on a variety of 12 supermarket objects which were picked up from the floor and no aids given to grasping. Disturbances were not applied in this experiment, however the object should still survive the gripper shaking and moving. The results over the 12 items are shown here. The same colour coding is used as before, with 10 out of 10 being the best score every grasp succeeded. Notice first the high scores for the fruit and vegetable objects, even with their rounded bottoms. Since they were low weight, grasping was much simpler than the first experiment. Next, the tomato jar and milk carton were only successful half of the time, depending on whether the finger hooks could slip underneath them. Finally, the tins and passata had the worst score, due to their high weight and the fact that grasping is impossible if the finger hooks cannot slip underneath an object. To conclude, Experiment 1 showed that the gripper was effective on elementary objects, with every shape being grasped reliably. Grasps used 2 mechanisms, firstly the fingers as a caging barrier, and secondly the palm squeezing for friction. Friction led to very secure grasps. However, caging led to less secure grasps, with the fingers being pushed aside by the disturbances since they were not stiff enough. Experiment 2 showed that the lightweight rounded bottom fruit and vegetable items were simple to grasp, whereas the key weakness of the design is that the finger hooks are not always able to slip under some objects. Future work will include refining the design, improving features, adding sensing for feedback control, and working towards further testing and autonomy. Thank you very much for listening.